Okay, pleasure to be here. Just arrived yesterday. It was a Jewish fest we do once a year to remember all the bad things we've done, so I hope I'm done with that. Today I'll be talking about processing technologies for specifically for deep learning, targeting edge devices. This is what Hailo does. We build processors. I'll do a quick recap of fundamentals of deep learning. I'll try to highlight the things that will be important for the rest of the talk. Then I'll give a specific use case, fairly simple, and I think for me at least it was a bit surprising to see how intense it is in terms of compute. And then from there I'll move to analyze different architectures that we see in the market and what they do better and what they do worse, and where are we now and where we should be. So a quick recap of the structure of neural networks. Neural networks is a family of algorithms inspired by neurons in the brain, but the mechanics are fairly simple. The basic unit is a neuron, which is basically just an element that takes a weighted sum of neurons from previous layers in the network, and then passes it through some sort of what you call an activation function, nonlinear function, to give some more generality to the structure. These neurons are formed in layers, and what gives deep learning the name deep is the amount of layers that are typically in a network, from a few tens to hundreds sometimes. The interesting thing to note is that the basic operation is the multiply accumulate. So this is a very good measure to how complex the network is. And what people call the type of layers is define the way that different layers connect to one another. It's usually a feed-forward network, so it's not a general graph problem. It's a directed acyclic graph. Also interesting to note that in many cases, the network is structured in a way that it can do multiple tasks based on the same front end, which usually is called a feature extractor, and then the output of which goes to different heads, which can do different tasks. And this is a very nice property because you can reuse your training and reuse your compute to perform multiple tasks based on the same network. I will focus on this talk on computer vision. This is by far the most, currently the most intense and interesting application for deep learning in automotive. There are many tasks which have been shown to work very well on neural networks in computer vision. A few common ones are classification. You're given an image and say, okay, it's a cat, it's a dog, it's a fish. Usually it's a cat. Another thing is object detection, which means that you have multiple objects in an image and you want to locate them and classify them. And a variant of that is the semantic segmentation, in which each pixel in the picture is given a topic, like a car, pedestrian, a lane, and so on. And these are all building blocks which allow you to perform more complex tasks. I'll give a relatively simple use case of a Rearview Camera. Okay, Rearview Camera installed in the back of the car. Usually, typical viewing angle is around 120 degrees. And three interesting applications which can be based on a Rearview Camera. So one which I'll give more attention to is the rear collision warning system. You used to think about this in the context of parking, but another important aspect which is currently not addressed is the case of a car coming to another car from the behind with high speed. This is, if you look at the statistics of accidents that are done by test cars for autonomous cars, this is one of the popular scenarios because they usually drive relatively slow. Another thing you can do with the Rearview Camera is to help you when you're changing lanes, to identify if you're going to do an accident while changing the lanes, and perhaps assist you with that. And third, parking assistant, which I think is relatively obvious. So, as I said, in many cases, the same head of the network, same feature extractor of the network can be used to different tasks. So, by analyzing one of them, you can get good ballpark numbers for all of them, I think. So, the scenario I've taken is high-speed cruising on a highway. You're driving at around 80 kilometers per hour, and the car is coming from behind at around 120 kilometers per hour. Taking your typical maximum acceleration numbers for relatively emergency braking or acceleration. In this kind of scenario, if you're the car that is going to get hit, you'd want to accelerate, not to brake. The system level requirement of this kind of task would be that it's always on, meaning it's always operating. what you're going to do with this warning, it relates to either what is the level of autonomy you're targeting. But if let's take a level 3, you'd probably want to match the speed using adaptive cruise control. And I've taken here a relatively typical safety margin of 2 seconds, meaning that you want to have at least 2 seconds before after you're dealing with a situation of margin between the two cars. So to achieve that, you need to identify, I'll save you the math, but you need to detect the car from around 50 meters. If you track the car that is coming from too far ahead, then you'll have all kinds of false detections because the driver might slow down. This is what would usually happen. But once it gets near the car, you need to track its speed to make sure that it's not going to hit you. So I've taken a relatively naive way of estimating the speed on which the car is detected, given a bounding box, and judged by the size of the bounding box, you can estimate the speed. Assuming that you are able to detect this to a passenger car, then you know more or less the dimensions of the car, and therefore you can deduce the distance and the speed. Now, to understand what kind of resolution you need for this kind of task, the question starts from how much pixels do you need to identify a car. This, of course, varies between different algorithms, but a typical number is a few pixels, so I've taken 8, and this would give a resolution of around 640 pixels. So we're talking about, bottom line, a VGA sensor. It needs to detect the speed of the car that is coming from 50 meters behind within something like sub-second. And within that period, it needs to detect positively 2 times the car. It's very simple and straightforward use case. A typical network that performs this, I think it was presented in the last talk in this room, would be an SSD detector, a single-shot detector. Taking this straight from the published article. It can be done slightly better at the expense of accuracy, but just to get ballpark numbers, we're talking about around 100 billion multiply accumulates per frame, which sounds maybe relatively high for some of you who are familiar with the numbers, for instance, of a VGG network, but take into account that the calculation is being performed on a relatively, it's not a very high resolution, but relatively high resolution. The numbers that are usually being quoted are on a 200 by 200 something pixel inputs. So in a real life scenario, you have a big factor in that just to accommodate for the larger aperture. So within these numbers, it's a relatively accurate network, and more or less, depending on what is the confidence level that you are asking for, you need around 8 frames to have a positive detection with good certainty. So putting all the numbers together, you're getting to a relatively high number of computation requirements, around 2 trillion multiply accumulates per second, which is a big number. Now, this is by itself doesn't mean much. The question is, what is the system cost for this kind of scenario? So there is a lot of talking about efficiencies of processors for deep learning. I'll try to give the baseline, what is actually achieved in reality. If you take just the baseline of doing the operation that I've given, the multiply accumulate, which is the operation of the neuron, take this into a digital circuit 60 nanometer process, very typical conditions, give this to a second-year electrical engineering student, you will arrive at something like 0.1 picojoules per cycle. So the inverse of that would be an expected efficiency of around 10 teramax per watt. So given the scenario of 2 teramax required, it would yield 200 milliwatt, which is surely not a problem. However, when you examine the result, these are all results that are publicly available on the internet by all these very respected vendors, where they publish what they actually achieve on real neural networks. I've focused here on image inference tasks, which are relatively well benchmarked. You see that the efficiency is less than 0.1 teramax per watt, which gives a really high number if you want to do 2 teramax. And data center class devices is, of course, normalized to the performance. Data center is slightly more efficient, mainly due to the use of batch processing, but not only. But in general, because of the scale, and embedded, it's definitely less than that. So bottom line, you get numbers which are definitely unreasonable just for a Rearview camera. Now, to understand where does the gap arise from, we need to go back to the fundamentals of how the new networks are built. So I'm going to give you a few very basic observations, very trivial, but often overlooked. So one thing is about the control structure of the network. Somewhat like a general purpose code, you want, when you're designing your network, you want to have lots of flexibility on the structure of the network. You want to have big layers, small layers, connected in all kinds of different ways. So you want very high flexibility there to optimize your model. On the other hand, once you have decided on the structure of the network, everything is fully deterministic. Things can be, I can tell you a billion cycles ahead what's going to happen in terms of computation. I cannot tell you the numbers that are going to flow through the graph, but the structure of the graph is static after compilation. So this fact can be utilized to our benefit. Second thing is memory. If you look at this structure of layers moving from one to another, you notice that the parameters which define the connections are extremely localized, and also the partial sums. The data that is moving in between the layers is not fully localized because it's shared between two layers, but still, on average, it's moving around 1 to 2 layers at a time. There can be also skip connections in these kind of networks. So generally, you have a strong sense of locality, and all of a sudden, the concept of a very distant, both logically and physically, central memory doesn't really map very well to this problem space. Third aspect, which is very well, I think, known, is the compute. You're doing, as I said, tons of multiply accumulates, and to a lesser extent, the nonlinear activations. The ratio can be 1 to 100 or 1 to 1,000, depending on the meta parameters of the network, but these are typical numbers. And most of the time, you're good with low precision. So 8-bit, we and others have very good results on 8-bit. However, in some cases, you do need higher precision. Let's take, for instance, I've given the detection example. So just to define the location of the bounding box at the edge of the network, if you're working on a full HD video, you need more than 8 bits just to represent the offset. It's something that, once again, on the research level, which is focused on relatively low resolution images, is not really taken into account, but in real world scenarios, it's really important. And fourth thing is to connect everything. It's very easy to optimize each one separately, but to have everything working together is, of course, a more complex issue. Another aspect, which is also, I've not seen any mentions to this in the literature, is that the structure, the fact that the structure of the neural networks is known in advance can play to our hands. And this relates to the resource balance along the network. The network computation is sequential. So each and every time you're doing something different, but you know what you're going to do. And if you look, they've taken here two typical networks, GoogleNet and ResNet, and just calculate layer by layer. This is the x-axis is layers. The ratio between how much memory you need to do and how much compute you need to do, you see that these are changing by orders of magnitude. So if you're taking a one-size solution to fit all, you're, in most of the time, highly inefficient. Okay? This is true in general in computing. You don't know what's going to come, but in this case, you do know, and you can use this to your advantage. So very broadly speaking, there are, I think I've categorized the market into 3 design philosophies. Okay, and of course, there can be hybrids. The first one is the fixed function accelerator, which means I'm usually synthesizing directly the RTL to match a network. Usually, there's some control on the parameters of the network, allowing you to retrain, but the structure is rigid. Definitely, this would be the optimal solution for a specific workload. However, taking a system-level view, the workload is often unknown when you're designing your chip, and you want to have lots of flexibility for advancements and further features along the way, so it results usually in a very low efficiency on the overall task. Among the programmable approaches, I think there are 2 opposites. One is the von Neumann architecture, the well-known von Neumann architecture, which is by far the most dominant form of computing. I'll try to give it from a neural network perspective. There are many aspects, of course, to this architecture, but one is that you're doing your resource allocation to different layers in the network in a temporal manner. You're doing one layer by the other. The second thing, this goes back to what I said about memory, is that you have central memory space, maybe with a few levels of caches, but generally central logical memory spaces which everyone can access and everyone can write and read from. And this, of course, creates a sort of a mesh architecture, end-to-end connection. The biggest advantage of the architecture is that it is well established in terms of programming model. We know very well how to program this. The C language prototype doesn't have to be exactly by the standard, but once you have this kind of processor, you can have lots of guys which will program it. Never mind if you have a different instruction set architecture or something like this, the model is well known. The sort of opposite to that would be the symmetric data flow architecture, which was suggested by I think multiple players in the market. And the idea there is that you have a simple element, think of an ARM Cortex M0, or it doesn't have to be exactly like this, which you're replicating by the thousands. And then you're doing a spatial resource allocation, meaning the first layer gets 20 resources, the second layer gets 40 resources, and so on. So you're balancing your computation between the different elements. This is to the extreme. If you think about it, it's like an FPGA. Usually, these are more aggregated elements. One thing that is created here, and once again, it's a side artifact, is that the memory space is now segregated. You cannot access different parts of the memory from different control and compute elements. So this plays to your benefit because you have locality, but on the other hand, now you have a problem of connectivity. And if you think about it in mathematically, this is probably the, I guess, sort of the ideal solution for a balanced, fully connected graph problem. Okay, I have not proven this, but it is intuitively, it seems right. Everything is balanced, and so this would probably be the best solution. Now I'll try to highlight some deficiencies in the architecture, and I think that if we're able to overcome them, we'll be able to gain back much of the gap between what we are achieving today into what can be achieved, which is said around 1 to 2 orders of magnitude of power efficiency. So first, start with the von Neumann architecture. I think the first thing to look at is the control. We're fetching instructions usually cycle by cycle. This is something which is very nice and very convenient in terms of software development. However, it is very expensive. You're paying it throughout all your design. I think there's a talk by Bill Daly, NVIDIA CTO, which estimates this to be around 90% of what the processor is doing is just being able to control itself. So as I said, in this specific scenario, it's definitely unneeded. Second, you don't often think about it this way when you're designing in a computer, but you're fixing the ratios between your control logic, compute logic, and memory bandwidth. You can add as much memory as you want at the outside, but the bandwidth is fixed, and the logic is also fixed. And now, we go back to the graphs I've described of how the problem changes along the network, you realize that there got to be some deficiencies in these choices. So either you're paying too much on some of the resources. And third is the concept of the memory. It's built just the opposite way than what you'd want it. It's relatively very narrow, even if the widest interface, let's say 1,000 bits, casting this to a trillion operations is relatively narrow, and it's very deep. A neural network, if you look at the model, I know people are used to thinking about memory footprints, which are very big, but if you look at this is a result of the implementation, not of the algorithm. The algorithm itself is usually a few megabytes, maybe a few tens of megabytes, so you don't really need this kind of deep memory if you're building things the right way. So this is the von Neumann architecture. The sort of opposite is the symmetric data flow. As I said, replication of multiple elements. You would want to have as many of these as you can, and the reason is to make the spatial allocation of the problem efficient. If you're too coarse-grained, you can't map your problem to different elements. So this is one driving force. The other driving force is that the smaller you make the element, you're paying more for your control logic, which is always there, and for your communications overhead. If it's a mesh connectivity, if you're not using the fact that it's not a general graph, then it doesn't scale linearly. It scales quadratically, and that limits the practical implementation of this kind of architectures if you look at examples that have been published to hundreds, maybe 1,000 cores, which is a relatively small number compared to the numbers that I've given, even for small-scale problems. And the other thing, which once again is not usually looked upon, is the fact that you have fixed memory space per compute element. And now if you need another place, it's very expensive to get it. On the other hand, you know that the problem is not symmetric. So you have very serious issues with scaling to different resolutions because you've chosen your memory to contain intermediate buffer, of some sort of size. And in this case, it will be hard to utilize it. On the other hand, you can't pick a memory which is too big because it will be extremely expensive. So this is I think the deficiencies in the symmetric data flow architecture. Now, going back to the overview that I've given, from our analysis, these numbers, even given all these limitations, these numbers can improve by around half an order of magnitude, give or take, meaning for data center, they'll be somewhere around here, and for embedded, somewhere around here. And I think this is what's going to happen in the market in the next, I think, year. You can see, by the way, representative of the last generation, which is the Myriad 2. There's already a Myriad X, which is about to be available, and this will align with the others. But still, these numbers are very, very far away from what you need. I've put in the red dashed line the 2 teramax line. So if you want to do this task with around 1 watt, which is a good number for embedded systems, we need to improve an order of magnitude or even more. And this is just for a rear view camera doing fairly simple stuff. If you want multiple sensors, high resolution, definitely we want shorter latencies if you're talking about level 3 and above. So this will not suffice in a realistic scenario. Another aspect of this is that to fit to these, and I think you've heard these kind of talks, to fit into these resource limitations, we are paying a lot today on software development, optimizing and squeezing things to fit into the current infrastructure. If you take an analogy to I would say the mobile world, this has lots of resources. You can start building a reasonable application without too much resources, and this is how you would want this world to behave in order to evolve quick. And don't forget also, we need to support this for years, these kind of version updates and things like this. I'll say a few words about, we will be launching our device next year, hopefully. And we hope to make this kind of task more reasonable. This is based on the first device we're going to use. And specifically for this use case, we expect this to be less than 1/5 of our processing power and overall power consumption of 2 watts, something that can fit directly into the Rearview camera and definitely at a reasonable cost. So this is what we and others hope to bring to the market next year. Thank you.